we will utilize these symbols all throughout the year. Guys, the first four, these represent states of matter. They will come after substances as subscripts. You've probably seen certain examples already that we've had in the past that have had those. We didn't talk about them in detail, but now we are. If you see an S or CR, that means you have a solid or crystalline state. L means liquid. Little g means gas. And then AQ means you have an aqueous solution. We have a whole unit on solutions later on in the year where we will talk about those more specifically in detail. But those ones are states of matter. And they can be anywhere. They can be on the left-hand side or the right-hand side. So in a reaction, what do we call the pieces, guys, that react together? Reactants, okay? Reactants react together to what? They form products, all right? So how we know where the reaction takes place, guys? Over here on the right-hand side are our reaction conditions. The arrow. Okay, this arrow is the key piece. That's where you know the reaction has taken place. The left-hand side of the arrow are reactants. The right-hand side are products. All right. Now, continuing back here in the left-hand side down these last two arrows, guys, but I want to talk about the reaction piece first for the arrow. You will only see these two pieces, these two symbols, only in the product side. All right, only with the products, because it says a solid precipitate forms or a gas product forms. So they will only be ever seen in the right-hand side of our reaction, the product side. All right, the other arrow symbol is very similar, is a double, which means you have a reversible reaction. They can reform. All right, so it's reversible. Later on in the year, especially when we get to acids and bases, we'll see the double arrow a lot more. Now these last several arrows, guys, again, means the reaction is taking place, but there's certain conditions under which the reaction has to be set at for the reaction to actually take place. So the first one, you've got the delta triangle, or heat. They mean the same thing, guys. The reactants are heated, and they need some extra energy for the reaction to take place, so it's heated. If you see some value like with kPa, or it could be ATM for atmospheres, that means a specific pressure where the reaction is carried out. Another number you can see with something like degrees Celsius, guys, we know what degrees Celsius means. So that's a temperature at which the reaction is carried out. Now, we probably won't see a lot with pressure in this unit because we don't know all the units for pressure. When we get to our unit on gas laws in semester 2, we'll learn all the different units for pressure, which will make it a lot easier to see and understand. All right, but temperature, you definitely could see that. Everybody knows degrees Celsius. Okay, no big deal there. If you have an element or a compound above the arrow, it could be or a compound, that means you have a catalyst. So you could see something like this as well. Let's say KMNO4 is just an example. It could be an element or a compound. That means you have a catalyst there. And then the last one, you have this electron symbol, guys, which is electrolysis. What does that sound like? Electricity, guys. So there's been some charge that's been added to get the process to speed up. Claire. So symbols, learn those. Moving on, guys. Chemical equations and reactions, they represent the known facts, all of our reactants and products, the pieces that are reacting together, and then what they form once they're manipulated. They contain correct formulas. Correct is the key word there, meaning what is crucial? Naming is crucial, folks. So guys, naming is crucial. Why this is so important? Our unit that we're going to do after break, stoichiometry, it combines units 5, 6, and 7, naming, the mole, and reactions. It all comes together. All right. So if you have not mastered naming, it's not going away. Going from names to formulas, and that's something we'll see here today. Coefficients, guys. Where do we see a coefficient? We've already talked about those. Not math class. I'm talking about in this class. We've already seen a coefficient before. In this class. Does anybody remember where it is? There was a 5, right? It was with a specific compound. Anybody remember what that compound was?
H2O.
It had H2O after the 5. It was a hydrate, copper 2 sulfate pentahydrate. But what did that coefficient really do? You multiplied it out to all the other subscripts, guys. So we use coefficients. We're going to see how we use those here when it comes to balancing. They represent our number of moles. All right. Subscripts in a formula will never change. Why do you think the subscripts will never change? If you change a subscript, what do you change? Not the amount you have. If changed, what else is going to change? The substance, guys. If you change a subscript, the substance itself changes. So as we go to balance equations today, we will never change the subscripts in a formula. They're off limits. Okay? The only time we will change them is when we're talking about reaction prediction. We have to make our products from our reactants. But when we're balancing, we only use coefficients to balance. Right? The numbers out in front. That's what we're going to practice here today. Alright, so as we balance equations, guys, there are 7 elements, 7 molecules we have to memorize and remember. Alright, because they exist as what are called diatomic molecules. What does di mean? 2. So they exist in pairs. Alright? They occur in pairs in their natural state. So they are iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. Alright? You may see those on your quiz within other examples. Alright? There's different ways. There's many ways you can memorize these and know them. These 2 phrases, to me, they don't make sense. So this is not how I learned them. I bring clay for our new house. I mean, I've never heard of anybody bringing clay to their house before.
His brown clown found no orange.
His brown clown found no. That's too long, guys. I'll get your question in just a second. The way that I remember it is this: Brinkelhoff.
Oh yeah, that's that.
Brinkelhoff. Okay? It's all of the symbols of those 7 elements written out. And it's a little bit easier to say. Again, this is why I think it is. It's the way I learned it so long ago. Find a way that works for you. There's many different ways. Okay? Find the way that works for you. Now, you may be asking, what's your question there, Yash? Of course you will. On what quiz?
Like the one with that in it.
The one with this? I said this would show up on Friday's quiz. I may have a section where I give you what are the diatomics.
And that one, but we won't have a...
You shouldn't need a periodic table at this point. No. You know what those are. You should.
Yeah.
Plus, there's a periodic table up in the front of the room. You can look at. Yeah. Anyway, folks, find the way that works for you. Now, you might be thinking, why? Why these 7 elements? Why do they exist in pairs? Well, take a look at where most of those are. What group on the periodic table are most of them in? No, what group? Oh, good thing. We do need to do some review for this semester test. Yeah. The halogens, they're in group 17. Folks, what do we know about group 17 and the halogens? They're 1 off from 8, right? So they have 7 valence electrons, meaning they want to get that 8th valence electron very, very badly. They have a high electronegativity value. All right. Also, chem is Fon. Those 3 guys, FON, they're the 3 most electronegative. So all these elements that we have listed here, these Brinkelhoff ones, these diatomics, they have high electronegativity, guys. They want to be stable. They want to have that extra electron or 2 that they need to be stable. So they will do everything they can, whether they bond with something else or bond with themselves, to get to 8 electrons. That's why they exist as diatomic in nature. All right, because they are so wanting to bond to get to 8 electrons because they're unstable as a single element that they form a compound with itself, and they exist as a diatomic. So why I write it out like this with Brinkelhoff. The other way is, if I write that out, put that on my test, just write subscript 2's in there. When they're by themselves, not bonded to anything else, guys, not in compounds, that's their chemical formula. When they're by themselves, they have a subscript 2. All right, you have to memorize that. Even as we go through practice here today, we're going to see some Brinkelhoff elements. From here on out, the rest of the school year, find some way that works for you to memorize those 7. For me, that's Brinkelhoff. All right, I've heard it makes a 7 if you look at the periodic table. Remember hydrogen and then 7. NOF and then down group 17. Whatever way. The 7, right, there's 7 diatomics. It makes a 7 on the periodic table. All right? Find some way that works for you. There's many different ways you can memorize them. All right, so let's talk about balancing equations. So we're going to get to today. Some of you may have already done this in middle school. I don't know. I didn't teach you in middle school. All right, depends on if your teacher taught you this. So we are going to be on the next page in your packet. Guys, when we balance equations, whatever is on the left-hand side of the arrow, you've got to have the same number of elements on the right-hand side, and that's because of the law of conservation of matter. All right, the law of conservation of matter must be satisfied. Matter cannot be created or destroyed in ordinary chemical reactions. All the reactions we're looking at are ordinary chemical reactions. The ones that aren't ordinary are like things like the atomic bomb, nuclear chemistry. All right. So what we need to have is on both sides of the equation. What's going to split the equation to mean when I say both sides? We already talked about it a few minutes ago. The arrow, right? That arrow, guys, it's separating the reactants from the product. So your reactant side of your reaction has got to have the same types of elements and the same number of elements as your product side. All right? And that's what we're going to kind of get into. So I've got some kind of rules, quote unquote, or steps of how to balance the equation. All right? The more practice you do, the easier it gets. Don't make this harder than it needs to be, folks. So, step 1, you're going to start with the word equation. If you're given a word equation, meaning I say hydrogen plus oxygen yields water. You would have to go from the words, write the equation, the formulas out, and then start to balance. If they don't give you the word equations out, then you're going to start balancing right from there. Don't forget your diatomic molecules when they give them to you in words. Okay? Meaning when you write them by themselves, those 7, they have a subscript of what? What's their subscript if they're diatomic? 2. So then when we balance, guys, we use coefficients. Do one element at a time. If you have a polyatomic ion, I highly recommend that you balance that together as what I call a package deal. If you see the polyatomic on the left and right-hand side of the arrow, balance it as one one entity. All right, makes your life a whole lot easier. Save oxygen, hydrogen to the last. Check, guys. Make sure you reduce your coefficients down if possible. Chemists are not in the habit of throwing away money. It's the opposite. They want to make as much as they can. So they won't want to use a higher number of moles than needed in their process, right? Because that's what coefficients represent, is the number of moles of each substance that we need to measure out. Never change subscripts. If we change subscripts, what do we change? The substance. Just like, guys, if we change the number of protons, what do we change in an atom? You change what atom you're looking at, what element you're looking at. All right, same type of idea that we've already talked about. All right, so I want you guys to write this order down. You can put it on the front page or somewhere where you have space in your packet. Now, this is no, kind of set law or rule here, guys. This is the order that I have come up with that I've kind of found works best for me to, 1, get me to the right answer, and 2, make it go as fast as possible. All right, so over the past 10 or 12 years that I've been balancing equations, this is what I have found to be the most efficient way to balance them as quickly as possible. Start with your metals first. Then, if you have any polyatomics, balance those second. Then all your other non-metals except for oxygen and hydrogen. Save oxygen and hydrogen until the very end. Why might we think that? Any idea? They're diatomic, so they could be by themselves. That's part of it. Well, and any compounds that contain water, that contain oxygen and hydrogen. Yeah, water. There's a lot of times you're going to have water by itself in reactions. It's a byproduct. All right? So saving hydrogen and oxygen till the end, if you balance everything else first, a lot of times the oxygens and the hydrogens are already balanced for you. If you start with those, you're going to have to go back and rebalance them over and over and over again. Highly recommend that you use a pencil. when you are balancing equations, because you're going to be doing a lot of changing and erasing. And if you use a pen, it's going to get very muddled and it's going to get very confusing very quickly. Let's just jump in, guys. I can talk at you all day about it, but let's start going through the process. So, very similarly to molar mass, we're going to write down and kind of bookkeep what elements we have. Today and even tomorrow, guys, we'll be writing down the work. You want to practice enough to where you can balance by sight. By next Tuesday's test, you want to be able to balance just by looking at it. Okay? If you don't get there, it's okay. Write it down. But if you balance it incorrectly, everything else from there could be off. So, write down what elements you have. I've got phosphorus on the left, and I have oxygen. Those are the only two elements I have. So what elements should I have on the right-hand side? Phosphorus and oxygen, guys. I should have the same elements on both sides of my arrow. Now, in this example, I went from left to right kind of listing them. Phosphorus and then oxygen. In this example, the right-hand side lists phosphorus and oxygen in that same order. Guys, it doesn't matter what order you list it in. For me personally, when I'm setting it up like this and showing my work, I want to have my same elements kind of on the same plane. What I mean by that is I want phosphorus across from phosphorus. I want oxygen across from oxygen. You don't have to draw those lines in there. I was just showing you. I like to set it up that way, and you'll see me go through that. Well, all right. List how many you have. How many phosphoruses do we have on the left? How many oxygens on the left? How many phosphorus on the right? How many oxygens on the right? All right. So now we've got to balance our equation. Meaning, what are we going to use to balance? Am I going to change the subscripts or am I going to use something else? What's that something else? Coefficients. Where do they go? In front, guys. They're big numbers that go in front. So I've got to get my left-hand side, my reactant side, to be the same number as phosphoruses that I have on my product side. Does 1 go into 4? Yeah, right? So I'm going to make a 4 there. If I put a 4 here to balance them out down below, what number has to be my coefficient then? Meaning 1 times what equals 4? 4. So that's what I'm going to put up there in front of P. I've got 4. Okay? I can change my coefficient because the coefficient represents the number of moles, folks. So in a lab, I can go and get more moles of a substance because I can go and get and mass out more of my substance that I need for my reaction. If I change my subscript, I'm changing the complete substance. That's, again, why we use moles, because it's our counting unit. All right, now oxygen's a little bit harder. Does 2 go into 10? Yes. So we know it's going to be 10 here. 2 times what equals 10? 5. So where am I going to put that 5? Right, that's the coefficient. All right. There it is. My final answer, guys, is this right here. I've got a coefficient of 4, 5, and then 1 in that order. How many of you guys have done this before in like middle school? About half of you. That's what it was in my last class as well. All right. So for those of you who've done it already, should be a review, should be a piece of cake. Do we understand kind of what I just went through with that first example for those of you who didn't do this before? All right. Let's try another example. It gets a little bit more challenging. All right. Write down elements we have. We got sulfur on the left, and we have oxygen. So I should have the same on the right-hand side. Do I? Yes, I do. Count up how many you have. How many sulfurs on the left? How many on the right? How many oxygens total on the left? How many oxygens on the right? Okay, so start with what types of elements first? Metals. Do I have any metals? No. Next would be polyatomics. Do I have any of those? How do I know if I have a polyatomic usually? Parentheses. Okay, so I don't have any of those. So now I'm going to go to my other non-metals, and like Darius said, we're going to start with sulfur. Save oxygen. Guys, notice, where do you see on the reactant side oxygen's in how many places? It's in 2 different substances, guys. This is another reason why we want to save oxygen and hydrogen until the end, because a lot of times they will be in multiple substances. So saving them until the end, if you save them to the end, it may make our lives easier to balance out, or they can just be balanced out already by taking care of everything else. So we'll start with sulfur. Sulfur balanced? Yes. All right, so now we have to go on to oxygens. Now, 4 and 3, right? One doesn't go into the other, right? So let's find a common multiple. What's our common multiple between those? 12. All right. So if I want to get oxygen on the right to 12, now I'm starting on the right-hand side, guys, because the left-hand side has got oxygen in two places. All right, it's a little bit more difficult, so I'm going to start with the right-hand side first, where there's a single oxygen. What coefficient do I need? 3 times what equals 12? 4. So my coefficient is going to be 4. By me putting a coefficient right there, what else did I now change? So I've got to go back and balance sulfur out, because now I have 4 sulfurs. You see what I'm saying? So how am I going to balance out the sulfur on the reactant side? What do I need up in my equation? A 4. Now what else did I change by putting that 4 there? Number of oxygens. How many oxygens total do I have on the left-hand side now? Really? 4 times 2 is? 4 times 2 is? 8 plus 2 is? So I have 10 total. Stick with me here, guys. Because I have 4 times 2 there. That's 8. And I have 2 here I've got to also take into account. Does that make sense? So, I've got 10 on the left. Well, I need to get it to 12. I have 2 options, guys, of oxygens that I can change. Do I want to change this oxygen right here? Because what else will I change? Sulfur. Can I change this one very easily? Yes. Absolutely. So I have 10. Now think about this, guys. 4 times 2 is 8. That means I need this one to have how many? 4. So what do I do to get this to be a 4? I put a 2 there. Now I have 12 oxygens on both sides. Do you see what I'm kind of getting at here? Guys, it's kind of a give and take. You'll find the way that works for you, but you're trying to get them to balance out on both sides. I'll get your question in just a second. Last step is to do what? Is this what I'm going to go with? We want to make sure our coefficients are what in the end? Simplified, folks. We don't have to use 4 moles of SO2 and 4 moles of oxygen to get 4 moles of SO3. We can reduce those down to what? 2 SO2 plus O2 yields 2 SO3. If we go back through and count those up, I've got 2 sulfurs on the left. I've got 2 sulfurs on the right. How many total oxygens do I have on the right-hand side now? 6. How many total do I have on the left? 2 times 2 is? 4 plus 2 is? It's balanced out, guys. So we reduce down at the end. All right. I want you guys to try this example on your own. All right. I want you guys to try this example on your own. Another example here. So that is how you should work that problem out. This one, I'm going to have to rewrite this one. We have a polyatomic here. So as we're listing our elements, we want to, if you see the polyatomic, guys, on both sides of the reaction, okay? One, if they don't have parentheses, you should put parentheses around it. But if you see it on both sides, keep it as one entity. All right, so we're going to balance NO3 as NO3. We're not going to break it up into nitrogen and oxygen. You can. It may make your life a little bit more difficult. I like to keep them together if I see them on both sides. If I don't see this polyatomic on both sides, then I have to break it up. All right, but I like to wait until the very end to do that. So I'm going to list them here, just like so. So this is what you would be like if you balanced it out. All right. Now this next one, we've got the word equation. All right, so first things first, guys, what do we have to do here before we can balance? We have to write the equations. What's water? H2O. Now when it says breaks down in the wording, what do you think that symbolizes? That's your arrow, and it is a decomposition reaction. We get to reaction types tomorrow. That is something that it's talking about. But guys, whenever you hear those type of key words, that means you have your reaction arrow. Hydrogen, how do we write that? And then oxygen? No, that is incorrect. Okay, it's still incorrect. H2, guys, these are Brinkelhoff. These are diatomics. This is why you've got to memorize those 7. You have bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Guys, when they are by themselves, like their name is there in the wording, that's when you have to write their formula with a subscript 2. Now you guys can go ahead and balance it. This is what you should have if you check your work. Your coefficients should read from left to right. 2, 2, 1 is what you should have. Questions? Easy? All right. Try the next one, guys. Methane gas is CH4. Write the equation out and then balance. So here, guys, in a problem like this, if they give you the states of matter, you need to put those symbols in along with it. All right. At this point right now, we don't know how to figure it out on our own, but if they give it to you, you need to write those in there. Now, vapor, what does water vapor mean? Well, it's H2O, but what does vapor imply? What state of matter? It's a gas. All right. I just wanted to point that out, guys. Vapor implies gas. So go ahead and balance this. So I would start with carbon. Carbon's already balanced. All right. Then I've got hydrogen and oxygen. It's a little bit challenging there. It doesn't matter which order. I'm going to start with hydrogen because it's a little bit easier to get those two balanced out. This needs to be a 4, so to do that, I'm going to put a 2 up here. All right, which then means I'm good for carbon and hydrogen. Now, by putting a 2 next to water, I've changed my total number of oxygens on the right. How many oxygens do I have on the right now total? 4. Well, that makes this a lot easier. This can be a 4 by putting a 2 right there. So it's 1, 2, 1, 2 is what our coefficients would be. Questions with that problem?